In this lecture, we'll be covering the topic of maximum likelihood estimation. Here is our setup. We have a vector of data, y1 through yn, and then we have a vector of parameters. So these are parameters for a distribution. If f is the density of y, and it depends on theta, then we define the likelihood function, L of theta, as a function of the parameters theta with the data y fixed. The observations are fixed. And we define our likelihood function as the density evaluated at the observation points in y with theta, the parameters for your probability distribution, being the unknown, being the independent variable. So you can think of this likelihood function as, it's clearly aptly named, it's the likelihood of the sample y. So if you think about what a density function actually is, we think of a density as a way that probability is distributed. So we have an area underneath the curve of 1. And of course, in this case, we have an n vector. So I'm simplifying things a bit because this would be the space Rn down here. And the idea is that we have this one observation. So this bold y is a vector in Rn. And it has some value when we evaluate the density function at that point in Rn. It has what you can think of as a probability associated with it. And we interpret that as, if you believe that this is the true density function from which this vector was sampled, then this value of the density function evaluated at y is actually the likelihood that that sample vector appeared according to this probability distribution. And the way we're going to think of this now is this y, again, is fixed, but it's the parameters of the distribution, theta, that are our variables, these elements of the theta vector. And so we can adjust or change the values of these parameters, which will move this density function around. It'll change the shape of it. And that gets us to this idea of maximum likelihood, where we say the maximum likelihood estimator is the value of theta that maximizes the likelihood function L of theta. And we denote it by theta hat sub ML. So let's recreate that same kind of picture. So we have our y vector coming from Rn. And we had our density function. The way we drew it before, I kind of drew it on purpose so that it wasn't going to match up with exactly what we want. So again, this is our density. And what we want to do is change the parameters of the density function to make this sample, this y, our data, as likely as possible according to this distribution. In other words, we fiddle with the parameters to maximize the likelihood of this particular point showing up. Now, in this version, that doesn't look maximal. We have a peak of the distribution over here. So what we want to do is change the parameters so that we get that maximum point happening. I didn't draw it very well, but this is where you want it. So the key thing is that we've assumed a family of distributions, or family for the distribution. So, we know that the distribution has some specific set of parameters, and given that data, that observation, we change the parameters to get that peak to occur with our given sample. Kind of the spirit of this is that if you truly believe your sample, if you believe your sample very well characterizes the distribution from which it comes, you sync the distribution up to that sample and say, okay, let's just say this is as likely as possible of a sample, and you calibrate your distribution to that principle coming from your data. Now, we are maximizing the likelihood function, which again is maximizing the density, but it's often much more convenient to take the log likelihood. And if you think about the natural log function, the natural log function is a strictly increasing function, which means if you compose it with the density, you will obtain the same maximum likelihood estimate of the parameters, of the independent variable, whether you maximize the likelihood function itself or the log of the likelihood function. So it's often easier to maximize the log likelihood than it is the likelihood. Not always, but often is. And this comes from the basic principle that logs will turn products into sums. In particular, as we will see in the next theorem, if your data are independent, you have a very nice property in terms of the density function. So let's illustrate that in an example. Suppose you have n normal observations, y1 through yn, all coming from the same normal distribution, mean, mu, variance, sigma squared, and they're independent. If that's the case, we know the density for each. So phi of x, this is the density for the standard normal, 1 over root 2 pi e to the minus x squared over 2. And if you want to get the density for each of the yi's, you take that normal density, multiply by 1 over phi, and then feed it this z-scored, so mean adjusted divided by the standard deviation term, x minus mu over sigma. And now we're talking about dealing with a distribution, one distribution, the normal, with two parameters, mu and sigma squared. So those are the parameters that form the elements of our theta vector. If you have n independent random variables and each has a density function, so your xi has its own density f sub xi, then the multivariate density function for the x1 through xn, thinking of it as a vector, our multivariate density is the product of the individual densities. And again, the key thing here is that these are independent. So in this case, in our example, we have a density for each y. It has this form. So when you combine this with this expression here, you get 1 over sigma root 2 pi e to the minus x minus mu over phi squared over 2. So the result, that this is that density. This is the density of yi. And using that result, that theorem, because our yi's are independent, the density of the entire random vector y is the product of the individual densities, which is what we have here. That's our likelihood function. So our likelihood function, the product of the individual densities evaluated at the data points yi. And again, our unknowns are sigma and mu. So if we simplify this, so we plug in to the normal density, the standard normal density, and we see here is our expression for the density for yi with phi removed. And we start to simplify this. So first, you have n products of this term out front. So that gives us a sigma to the n and a root 2 pi to the n. And then we have a product of exponentials, all with base e, which means that would be that exponential raised to the sum of these exponents. So we're simplifying a bit. The 2 sigma squared is coming out, and that leaves us with e raised to the sum of that minus 1 over 2 sigma squared times yi minus mu squared. Okay, so looking at this now from an optimization perspective, what we want to do is maximize this over the variables mu and sigma. Or equivalently, it's a little bit easier to do it this way. We'll consider it mu and sigma squared. But you see you have this sigma to the n in the denominator here, and then this sigma squared showing up in the exponent of e. This is going to be much more straightforward if we use logs to split this product into a sum of logs. So we transition to log likelihood. So when we take the log, the natural log of this likelihood function, first we get natural log of this term. So we have natural log sigma to the n, 2 pi to the n over 2, all to the negative 1. And then plus the log of the exponential. Those are inverse functions, so they undo one another, and what remains is what was in the exponent. We then change things a bit. Instead of sigma to the n, think of it as sigma squared to the n over 2, and we'll actually work with sigma squared instead of sigma. Either way works. You can work with sigma. You can work with sigma squared. You get the same result. The math's just a little bit nicer if we work with sigma squared. So this expression here now simplifies to sigma squared times 2 pi all to the negative n over 2. And now you see the payoff of doing that. We use the property of the log and bring the negative n over 2 out front. And then what remains is log of sigma squared 2 pi, and the log of that product is the sum of the logs. Over here, we don't really change things. So this is our log likelihood. This is what we want to maximize over sigma squared and mu. This is that same expression. And now let's notice where these terms show up. So first, there's a sigma squared showing up in these two terms. So there's a coupling there. But notice that mu only shows up in that one spot. So this term is unaffected by mu. So in order to maximize the log likelihood with respect to just mu, we can choose the mu that maximizes this second term, or equivalently, because there's a negative side, this sigma squared is positive, this sum of squares is positive. So this whole expression, when you're multiplying by a minus 1, is less than or equal to 0. So in order to maximize that expression with respect to mu, we want to minimize this sum. Again, mu doesn't care about the 2 sigma squared. Mu only affects this sum here. So let's minimize this sum. And again, we minimize it because there's a minus sign. Remember, we're maximizing the overall log likelihood. Well, what value of mu minimizes the sum of the squared deviations from the mean? The sample mean. So the sample mean, right, remember y bar is nothing more than the average of the yi's. Now, this we can consider a done deal. This is the maximum likelihood estimate for mu. So we now consider that fixed, and now tackle this in terms of the sigma squared term. But with mu fixed, this is now a function of one variable, sigma square. And our goal then is to take the derivative of the log likelihood with respect to sigma square, set it equal to 0, and solve. So if we do that, let's start here. So our first term, we have a minus n over 2, so that will stick around. So the derivative of the log likelihood with respect to sigma square, we have minus n over 2. And then we're multiplying by this natural log of sigma square. So the derivative of that with respect to sigma square will be 1 over sigma square. There is no sigma squared term appearing in this negative n over 2 times natural log 2 pi. So the derivative of that term with respect to sigma square is 0. Now here, we think of this as 2 sigma square to the minus 1, or maybe simpler, 1/2 times sigma square to the minus 1. And we take the derivative of that expression with respect to sigma square, which is a power rule problem. So that'll give us minus 1/2, that constant sticks around, and then we have times minus sigma square raised to the minus 2. And then, of course, this sum just behaves like a constant, so that sticks around. And so now we want to simplify a bit. This term will become negative n over 2 sigma square. This term will become positive 1 over 2 sigma squared times our sum. And we have this depicted on the next page. So this is exactly the computation that we just did. And we set that to 0, first order condition. So, to now solve this for sigma squared will result in this expression here. 1 over n times the sum of the squared deviations from the mean. Now, why is that? You can see if you clean this up a bit, say take one more algebraic step so we can see it, you'll have that minus n over 2 sigma squared. Well, if we bring that to the right-hand side of the equation, that becomes a positive. And here you have that negative times a negative, so 1 over 2 sigma squared times the sum yi minus mu squared. And remember, we have set this to be our y bar because we fixed mu. And now you see, you multiply both sides by sigma squared and divide by n, and your result is this expression that we have here. Now, why is this interesting? Remember, when you work with the normal, how do you estimate your mean and your variance? Well, for your mean, you estimate with the sample mean. You get an unbiased estimator of the mean. But remember, when you estimate the variance, typically you use the sample variance where we divide by n, and this is a sum, rather than dividing by, we divide by n minus 1 rather than dividing by n. And the reason for that is you want an unbiased estimator. And if you just take the average square deviations from the mean, you actually get bias in the sense that the expectation of that estimator, that maximum likelihood estimator, isn't quite equal to the variance sigma squared. It's adjusted by n minus 1 over n. So it's slightly biased on the downside because this is slightly less than 1. Think of n being big. It's like, 99 out of 100 times sigma squared. So this is a bit different. When you're using the maximum likelihood estimate given a set of observations for the normal, your estimator for the variance is a little bit different than what we're used to. And so that shows you, this is kind of the classic example to see, that number one, it makes sense because the way you're syncing up your distribution by fiddling with the parameters mu and sigma to this data is not that different than taking a sample mean and your sample variance. We see the sample mean is in fact the maximum likelihood estimator for the mean, but we see the maximum likelihood estimate for the variance is slightly different than our unbiased sample variance.